I'm going to take one more example to show another generalization which leads to another standard function. And we can motivate the standard function using a function called takeLine. So the idea of takeLine is to take the first line of a string. And what is a line? Well, it's everything up until but not including the new line character. Okay, roughly. There are actually many different variants on the new line character. I'm not going to worry about those for now. So a line is everything up until the end of the line. And what's the end of the line? It's just a particular character. It's the new line character. So we recursively keep taking the characters while they're not equal to the new line characters. You keep going recursively until either you hit the end of the list or you hit something which is a new line character or one of its relatives, but I'm not going to worry about that case. Either of those two cases are base cases. That's when you stop. Okay? And so if I take a line from the song, I get all the characters up until the first new line character, namely the first line of the song. And the function lines, we could build that on top of this function. We have to repeatedly take the first line, then the next line, and so on. But I'm not going to get into the details of that. That gets a bit more complicated. But I want to say, well, you know, this is not the only operation of this kind that you might want to do. You might also want to take the words. The words function. I don't know if you remember what the words function does. It takes a string and breaks it down into its individual words. And the way that this works is by grabbing all of the characters until it reaches either the end of the list or a space character. So the take word function, if we're going to define something like that, if you want to take a word from a string, then what it would do is something very similar to this guy, cut, paste, and you would take word here, but you would not be checking whether it's not equal to the empty. You would check whether it's one of the space characters. Now I said I could just check whether it's exactly the space character, but actually there are many different space characters, including the new line character is one of the various kinds of space. When you have a new line character, that's the end of a word as well, right? So we need a function that determines when a character is one of the possible space characters. So we could define that using the lm function to check whether a thing is in a particular list. But actually there's predefined functions for working with characters, lots of useful ones. If we want to find what they are, one way of searching for them is to use Hoogle. So Hoogle is kind of like Google. I mentioned it very early, but we haven't really used it much since. You can use it to search for things like map, but more interestingly, you can use it to search using types. And that can be really useful. And it does search in a smart way. So I'm interested in functions which take a character and tell me properties of those characters. I'm interested in functions of that shape. So if I search for those, it finds all standard functions which do these. And these are all living in a module called data.char. So they're not in the prelude. We don't get them automatically. We need to import them. And there's lots of them. IsDigit can be quite useful, actually. We'll probably use that at some point later in the course. There's millions of them. But this is the one actually I want, IsSpace. Returns true, so I can read it to you because it's very small. Here, maybe I can zoom it in a bit. IsSpace returns true for any Unicode space character, whatever that is. It includes the control characters. That's the tab character, \T, the new line character. And then on Windows machines, you tend to have these two characters, return followed by form feed for some historical reasons, instead of new line characters. Anyway, these are all considered space characters as well as the ordinary space. So if I want to use that function, I can import it. Now I can either import all of the functions from data.char, that's what I've done now, or I can just import the ones that I need. And sometimes that's better because it tells me, firstly, what I'm using from this module, and also make sure that if there are lots of names in here that I don't know about, I won't get strange error messages when I accidentally define a function with the same name as something in the module that I'm importing. So it can be good to be a bit restrictive. I've already imported data.list. I can't remember why. I don't think I've used anything from that yet. Okay. So where is my example? Oh yeah, it was is space C. Okay, so that was my take word function. I actually remember to rewrite all of those bits. So if I take word from the song, oh, that didn't look too good, did it? Something's wrong with take word. Ah, got my base cases the wrong way round. It's if it's not a space, that's when I want to take the character. So it's not a space. Don't think there is a function for that. Let's reload that. Let's try it again. Okay. I was the first word of the song. So I've written that in a slightly strange way, but that's because that's deliberate, because I want to introduce a standard function. And the standard function is one which generalizes these two. So what is different between these two? Well, here I'm checking this property, and here I'm checking this property. So I have two different properties here that I'm using to check whether to carry on grabbing characters or grabbing things from the list or to finish. Okay? So the thing that differs between these two is a predicate, a function which gives me a truth value. Now they're written in two different ways. They're not written just as function applied to argument, but basically what they do is they take the character and they give me a true or a false. Okay? So the general function is called take while, and it takes a property as its argument, and it takes the characters, the things from a list, while the property is true. And the shape of the function is very similar to this. So I will do a legitimate cut and paste. The two cases are the empty list and a non-empty list. And instead of this general, this not is space, we just take P of C. Okay? And instead of take word, it's take while P. So that's another example of a general higher order function. It's a standard prelude function, so I better rename it if I'm going to do anything with it. Oh, I forgot to write in the base case over here. Let's write it there. Okay, so that's fine. What is the type of take while? Well, it has two parameters. So it's a something arrow result. The first parameter is a function. It's a higher order function. And the second parameter is a list, and the result is a list. So that's the shape of the type. And you see that the type of the first parameter has to be something which gives you a true or a false. And what it will do is give it a list, and it will give you a list of the same kind, but maybe just the first part of that list. Okay? So if we wanted to define take word, instead of defining it in this way, we could have defined it using take while. If we have some string, then it's equal to take while non-space of that string, where non-space for some character is equal to, all right, that was probably a bit hard to follow. So we could have used it this way. We could have used this non-space guy. Space. Okay. So here we're feeding the higher order function by defining just the function we need. Okay. Any questions? All right. So this idea of feeding functions, that's one way that we can feed functions. We define the function we need and we pass the name of that function to our argument. But it turns out that there are lots of other convenient ways of defining the function we need without having to give a name to the function. So we can do the same thing without having to go through the hassle of defining a new named function. Okay? So I'm going to look at how we do that. And so what I want to show you is, the first thing I want to show you is anonymous functions. So here I fed this function by creating a function with a name. What if I didn't want to do that, if it didn't seem worth it? How can I define the function I want? Well, isSpace is not the function I want. I want the function which is giving me this thing for every character. So one way to do this is to define what's called an anonymous function, or it's also called a lambda expression, or in some programming languages they call it a lambda function. So I think in Python, for example, they would call it a lambda function. So this is historical. It goes back to the logical foundations of functional programming from the 1920s, something called the lambda calculus. So a lambda expression is a way of defining a function without giving it a name. Okay? So how do you do it? Well, you say, if you give me an argument, I have to give a name to the argument, C, the result I want to get from this function is not isSpace C. So that's a description of the function without giving the name of the function. Okay? So here's how you write that down. You say, if you give me a C, so you write backslash, which is a kind of way of indicating the lambda symbol, which looks a bit like a backslash. If you give me an argument C, this function will return the value of not isSpace C. And the reason I need brackets around the whole thing is whenever you write a function using this lambda expression notation, it assumes that it goes on until the end if you don't put a bracket in. So this thing does the same job as the previous one using an anonymous function, a lambda expression. So this is saying this is a function which says you give me an argument C and I'll give you back this result. Okay? Any questions about that? So sometimes it's useful, instead of defining a new function like I did here, non-space function, sometimes it's useful if you just have a very small function and you want to feed a higher order function, it's nice if you can cook that function on the spot rather than having to go and define it. Yes?
Can you define a recursive lambda function?
The question is, can you define a recursive lambda function? Not really. And the reason is because we don't have a name for the function, we can't call it recursively. So in the obvious sense, the answer is no. You can't define a recursive lambda expression. There is, though, however, a higher order function, which is kind of the mother of all recursion, which you give it, where you give it a function and it builds a recursive function out of it. But that's a different story altogether, and we're not going to go into that here. You might see that in the models of computation course later, where the lambda calculus is studied in a kind of pure sense. But yeah, basically, because we don't have a name for the function that we're defining, we can't call it recursively. So no, we don't use it to define recursive functions. We can use it to define functions of multiple arguments, and we can use it with pattern matching. In the case of pattern matching, it can get a bit complicated. So if you wanted a function with two arguments, for example, you could write it, one way of writing it would be C1 and C2. That would be a function of two arguments, which does this. Of course, that won't be type correct if I do it here. Okay, I'm not going to use it so often. Once in a while, it'll be just the right thing, and I'll use it. But it's not something we're going to use everywhere. And it's not something you have to use. You can always do it this nice systematic way, and you might find that more readable and easier to understand. And that's no problem. Okay, so that was one way of feeding functions, anonymous functions. I'm going to show you one other way, which is really intuitive, I think, and I think you'll pick up very quickly. And that's called something called sections, and that's a little Haskell trick. And I think to understand that, it's probably enough to look at some examples. So on the slide, we have some examples of using sections. So here, we're mapping the +1 function over the list. And what does that do? Well, it adds 1 to every element of the list. Here, we're filtering using the <0 function. And that will give us all the negative things in the list. Here, we're using that take while function, take while things are bigger than 0. So it'll take the first thing, but not the second thing, because that's <0. Okay? So how does it work? Well, it works by taking an operator. That's something which is expecting two arguments that you write on either side, like plus, with the two numbers on either side. But instead of giving it two arguments, you miss out one of the arguments. You leave out one of the two arguments. And what have you done when you leave out one of the two arguments? You've built a little function that's waiting for that second function. It's also a kind of anonymous function. But it's very practical, very convenient to build small functions. Okay? Any questions? Now, there's a limit to what you can do with this. For example, you might want to write the times 2 plus 1 function, which multiplies the argument by 2, then adds 1. But you can't do that. So you can't do fancy stuff like that, because that's somehow nesting one of these functions inside an expression, which is not a function. And so while it looks kind of intuitive, it doesn't make sense if you break it down into its individual pieces. So if you wanted that function, the way we would write it was using a lambda expression as one of the ways we would do it. Okay? Any questions? All right, so that was another way of defining, building small functions by taking an operator and giving it one but not both of its arguments. Okay? It only works for operators. Now you might say, oh, that's a shame, because there are lots of functions that could be good, but they're not operators. But actually, you can turn any two-argument function into an operator. Does anybody remember how to turn a function into an operator? You use the backward ticks. You remember the lm function to test whether an element is in a list. 1 is in that list, but 0 is not in that list. It can be hard sometimes to remember which order these go in, but if you write it using infix notation, you can write the function as if it was an operator by putting these backward ticks around it. You remember that? You're asking?
Is there a way to write it in postfix?
No, there's no way to write it in postfix. So this is a little bit of, yeah, you get a little bit of flexibility in the syntax, but only a little bit. There are a few research languages that have more flexible syntax where you can define things in other ways. But there's also something called macros, which are kind of like shorthands. These are not macros, but they do something similar. Okay, but because we can write this function as an infix operator, it means we can build sections from this. We can build a function by applying this operator to one, but not both of its arguments. Here's an example. Let's take 0 to 9. So that's a function, right? It's a function that's waiting for that first argument of lm. So this is the function that tests whether its argument is in the range 0 to 9. So if I apply this function to 0, yes, that's in range. But if I applied it to 10, it's out of range. Now, of course, I wouldn't write it in this way. It'd be strange to write it in this way. But if I'm trying to feed a higher order function, this might be just what I want to do. I might want to, for example, filter all the numbers in a list which are in that range. So one way to do that would be to filter using this function. If I take the numbers from minus 10 to 10, then it will only keep the ones which are an element of the numbers from 0 to 9. And that is precisely 0 to 9. Okay? So sections can be very useful ways of building just the function you need without having to write very much code. So when you get used to using higher order functions, it enables you to build useful code very quickly by reusing these standard computation patterns. It requires extra practice and extra skill to learn to use them. But once you've learned to use them, there is a payback that it accelerates your programming productivity. Any questions? All right, I want to talk about one more way of building small functions easily. I've talked about anonymous functions, lambda expressions. I've talked about sections. And now I'm going to talk about function composition. So in mathematics, you've seen function composition, I'm pretty sure. It's where you join two functions together to build one composed function. And in mathematics, you usually write it as a small circle in between the two functions. I think you maybe have seen that notation. Anybody, does that sound familiar? Okay. We don't write the small circle in Haskell, although I think you might be able to do that. But what you do instead is use the dot. So the dot, single dot, will be used to model function composition. So let me just refresh your memory of function composition, because Haskell function composition is really the same as mathematical function composition. The notation is just slightly different. Sorry, this is all a bit slow, this changing of... There we go. So here's one way of defining. I used this not space function in an earlier example. Not space of x is space, and then you apply not to the result of that. So another way of writing the same function is to write not space is the function you get by composing using function composition, that dot, the not function with the isSpace function. So let me just picture that. Don't quite know what's going on here. It's not showing me my screen, but let's just picture that visually. I'm seeing everything I want to see on this little screen over here. You could all just come down here and have a look. Let me just see if I can escape from this hell here. So my computer's decided that it's not happy. Okay. Maybe. Let me see. Come on. All right, let me do this slightly differently. Let's not bother about worrying about the... Right. Okay. Visually, isSpace is a function which we can view as a black box. You feed in things, I'm going to feed them in on the right, and they're going to pop out on the left. That's where the argument goes, to the right of the function, right? So it's going to go from right to left. So if we feed this guy with a character, then it will give us a Boolean value. So the type of this is char to bool. Okay? That's the input, that's the output. And the not function is kind of similar, but it's not the same type. It's a function that takes a bool as an input and gives a bool as an output. Okay? But because these two types match, we can plug these two functions together, right? We can take the output of this guy and feed it into the input of this guy. And that's what the function composition operator is doing. It's plugging these two boxes together. It's building that thing. Okay? So that's what function composition does. It builds a new function, that's that thing there, from two other functions by plugging them together. And so this composed function is written not composed isSpace. And that's why I've written the arrows from right to left and not left to right. And that's because you have to think of this as you're first applying this function and then applying the not function. So the notation looks a little bit backwards, but that's the way function composition notation works. Okay? You kind of have to think of it a little bit backwards. Any questions? So what that means is, if we go back to some of the earlier examples, actually we didn't need to use a lambda term here. Instead, let me just keep that. Instead, we could have just built the function we wanted by using function composition. It's the composition of not and isSpace. The spaces I've put here are not important, but it maybe is easier to read. Okay? So this is an operator for combining functions. Any questions? So is this dot, is that a built-in function of Haskell? Is that a special function, do you think? There's nothing special about it. It's just a function defined in the prelude. How is it defined? Well, let's define it. F composed with G is equal to what? What is it? It's a function. So I'm going to write it using lambda notation just to emphasize that this is a function. What does this function do? Well, if you give it an argument x, what it does is it first applies the function g to x and then applies f to the result of that. So that's a definition of function composition. Very simple. The only thing that's missing is the rules that tell us what the precedence of this operator is compared to the other operators, but that's not so interesting. And also whether it associates to the left or the right. Any questions? I can't do that because, of course, it's already defined, so that would give me an error. All right. So we've made some good progress. We've seen different ways of doing this. Now, because functions are first-class citizens, one form of higher-order function is to say we want to define a function. Here we wanted to define a function in terms of some other function. And in fact, that's something we can do with many of the functions we have. We can define functions in terms of other functions. Now that's going to be a bit mystical, so I need to talk about something called partial application. Here's a function which is not terribly interesting. It takes an int, a string, a character, and gives us back a string. So let's try it out. Let's see what it does. Rep 4. The second argument, first argument is an int. I've given it 4. Second argument is a string. Let's say hip. And the third argument is a character. Let's write the bang character. And what does this give me? Well, it gives me that string here. It's repeated 4 times. It takes the string and the character and repeats them 4 times to build one big string. So this is the way it was defined. And this is not important. What's important is going to be to do with what the meaning of this type is. Okay? So everybody can see what the function does. Okay? Now you think of this function as a function which has 3 arguments. You give it 3 arguments and it gives you back a string. But that's only one of the ways you can think about this function. You can also think about this as a function which has 1 argument. What does that mean? Well, I can think of it as a function that has 1 argument, an int. Let's try it out. I apply it to 1 argument. Well, that's not going to work because what's the result of that? What's the type of that? What's the type of rep 4? If I'm saying it makes sense, then it must have a type. It's a function. It's a function that if you give it a string and a character, it will give you back a string. So let's try it. If that's a function that if you give it a string and a character, it should give me back a string. Well, it does. Okay? So how is that different to what I wrote before? Well, it's not any different. It's exactly the same. When we write this expression, it's the same as putting brackets in. We didn't need the brackets, that's why we didn't put them there. But if we put them in, it would be the same thing. So when we have a function of more than 1 argument, we can always think of that function as a function which has 1 argument whose result is a function. So just like I put in brackets here that I didn't really need, I can put in brackets in the type that I didn't really need. Let me do that. You'll see that it doesn't make any difference. So rep can be thought of as a function which takes 1 argument and gives you back a function, which if you give that 1 argument, gives you back another function, which if you give it a 3rd argument, will finally give you a string. And that's what I did when I wrote it out in this way. I took it and applied to 1 argument, took the result of that, applied it to another argument, and so on. Okay, so what's the point of that? Well, it shows you that there's another way of building functions. You can build functions by applying a many argument function to some but not all of its arguments. So it's a bit like sections. So is there anywhere we could have done that here? Well, in fact, there is somewhere, and it's this take word function. I'm trying to define a function, take word. And the function I'm trying to define is the function which corresponds to this thing here. Take while applied to one argument is a function, which if you give it a string, takes the word from that string. So an alternative way of defining this would have been to say this function is equal to this function. And that is called eta conversion or eta reduction. We don't need to name what the argument is. We just say that this function is the same as this function. How do I know this is a function? Well, the type of this has two parameters, and I've only given it one parameter. So what I get back is a function. Now, these use of higher order functions can take a while to get used to. There is some assistance in the system that will help you learn where you can use higher order functions. And it's a tool that when you install GHC, you get an additional command. Instead of just GHCI, there is also a command called hlint. So hlint is a command you type at the terminal with the name of the Haskell file you want to check. Now I can check this from within inside my editor using this Control-C, Control-V. So I can show you what it usually does. Control-C, Control-V, hlint. So I get an output which gives me some hints about things relating to using higher order functions. For example, when I define sum this way, it says, hey dude, why not define it this way, using fold? That's quite useful. So this way, by running hlint, you can start to learn to spot standard higher order computation patterns.